Good morning, Physics 20s. What we're going to talk about today is the forms of energy, or I should say the various forms of energy that we're going to calculate, assess, and honestly think about and observe as we continue on our physics journey. You can think about energy is, in the very general sense, as existing in two different terms. The first term would be stored energy, where you don't see energy moving things or releasing heat or anything like that. It just gets stored up, kind of like a battery that's absorbing all the power. And in stored energy, we have a couple of subcategories as well. And then we have what we call used energy or useful energy. And that's the kind of energy that you would expect to cause something to heat up, to cause something to move, to cause something to wear down. And so in general, we have, like I said, we have stored energy and we have used or useful energy. And in physics, we narrow those down to stored energy being referred to as potential energy and used energy being referred to as kinetic energy. Now, when it comes to stored or potential energy, we tend to think about it in three subcategories. The first would be gravitational potential, and that is the effect that height has on an object's energy. So if I pull a chair up here and I stand up, just by me standing up from sitting down, I'm increasing my potential energy, or the effect that gravity would have on my body's ability to move downwards. Then when I climb on the chair, I've increased my potential energy again. Why? Because I have increased the height. There is an old saying that the higher you go, the harder the fall. And that is very, very true in physics, because the higher you go, the more potential energy your body is storing, which means that the more energy it can dish out once it starts moving. Then we have the second form of potential energy called chemical potential energy, and that's the energy stored in chemical bonds. And so when atoms bond together, there's a whole lot of energy there, and that's often the release of that potential energy is what causes explosions. Pretty good. Okay, so
No, right on top, like right there. This goes wrong.
Are you?
okay, hold on. Okay, so you ready? Okay, go.
Wait.
Allah Akbar. The last form of potential energy is what we call elastic potential energy, or some scientists just call it elastic potential. And that, again, similar to Hooke's law, it has to do with the work done by the restoring force inside objects, or elastic band, right? The more I stretch it, the greater the potential energy increases, which is why, it hurts when you snap it back. And of course, in the bow and arrow, where the more I could pull the string back, right, the greater the work is going to be done on the arrow, okay? And in the form of so it'll, as I pull this, my elastic potential energy is increasing, and then finally when I let go, I see a conversion to kinetic energy. So that sums it up. We have gravitational potential, we have chemical potential, we have elastic potential. What we're going to look at in this course specifically is gravitational potential and elastic potential. And the last type of energy that we're going to talk about and calculate in this course is the kinetic energy, or used form of energy. And essentially, once an object starts moving, and it starts moving at a constant speed, we say that the potential energy is being converted into kinetic energy, or it has kinetic energy. And so often we take the kinetic energy and we use it to find the speed that the object is going at. And often kinetic energy can also be referred to as heat. In fact, heat, as we learn in chemistry, is really just a specific form of kinetic energy. And so it is very common that once things start moving, they actually start to heat up. And that will lead us to the final part of this whole energy topic, which is the work energy theorem. But that's all for now. Let's get right into the math of it. Now what this machine is going to do is it's got a conveyor belt. So you'll have kinetic energy that is going to build into static electricity or static potential energy. And once there's enough buildup and I get close enough to it, the charges of my clothing and the charge that has built up, the static charge that's built up on this ball, is going to quickly convert the energy into more useful kinetic energy, and I'm going to get zapped. So now what we're going to do is get right to the formulas of these energies. So we mentioned that gravitational potential and elastic potential are the ones that we're going to primarily focus on. So let's start off with gravitational potential. Now we often denote gravitational potential with the symbol EP. Okay, and so gravitational potential is like it sounds. It's the potential energy that is gained due to the force of gravity. And so we're going to go EP is equal to the mass of the object multiplied by the gravitational acceleration multiplied by the change in height. Remember we said that as you increase in height, your gravitational potential increases, right? The higher you go, the harder the fall. It comes from this. So if we're going to quickly mention what each one is, this is your potential energy. This is the mass of the object. Okay, and the mass of the object should be given in kilograms. And this one should be given in joules. This is going to be 9.81 meters per second squared because we're going to focus primarily on things that are happening on planet Earth. And here, this is your change in height. So remember that delta H is really equal to the final height minus the initial height. And this is going to be in meters. The second useful form of potential energy is what we call elastic potential. And again, remember that this refers to the work or the energy that an object experiences due to the elastic force. So we're going to write here refers to the work being done by the restoring force. And so this is an extension of Hooke's law. So again, we say it's EP because it is a form of potential energy. But what we usually say, instead of writing EP, we could write E lowercase e, and this would represent elastic. And that'll be equal to half kx squared, where this is your elastic potential in joules. Your K is going to be the spring constant of the mass. And just like in Hooke's law, it's going to be in newtons per meter. And the X is the you could say the amount of distortion. Okay, so how much an object is stretched or compressed, and that has to be in meters. So which of these two do we use? Gravitational potential or elastic potential? Well, it really just depends on what the question is giving you. If the question gives you a height, then for sure we're going to use our gravitational potential. But if it gives us a spring constant and some sort of distortion, meaning that it indicates to us that it's being stretched or compressed, then for sure we're going to look for the elastic potential. However, and this is what we're going to write down, both of these energy forms can be converted into kinetic energy. So let's take a look at our first example. It says a 5.0 kilogram object is lifted up to a height of 1.5 meters. What amount of potential energy does it have? So first of all, what kind of potential energy does it have? Does it have elastic or gravitational? Well, since it's lifted up to a height, we know that it's gravitational. So we're going to use the formula EP is equal to mg delta h. And we're given a mass. We know that the gravity is always 9.81, and we're given a height. And when we say change in height, if they give you a height, we can assume that the initial height is 0 if they don't state it otherwise. So our change in height is going to look like this. We're going to go EP is equal to 5.0 kilograms multiplied by 9.81 multiplied by the difference in height, which is the final height of 1.5 minus 0. And when we plug this into our calculator, we should get approximately 74 joules, give or take. So you could say 73.6 or 74 joules. It really just depends on what the question is specifying. So the first one was relatively simple. Let's look at the next one. So we're going to assume, it says here, if the same object from the previous question, so the 5 kilogram bow, or not bow, but the 5 kilogram object, was found to gain a potential energy of 100 joules. So this time we're given our EP, and it's 100 joules. What final height was it lifted to from 1.5? So here's how it works. So originally, based from the last question, it was already at 1.5, and it got lifted to some sort of height, which we don't know, until the EP was 100. So what we're going to do is work backwards and find out what that height was. We're going to go EP is equal to mg delta h. EP at 100. Now here's the thing. Do we go for 100, or should we take the difference in potential energy? If we're trying to find the difference between this and this, well, then we want the change in potential energy. And so we're going to go like this. So we're going to write 100 minus 73.6 is going to equal mass times gravity, 9.81, multiplied by the HF, we don't know, but the HI we do know. Now what we have to do is isolate for the missing variable. So we're going to go 100 minus 73.6, and that's going to give us a potential energy about 26.4. So I'm going to write this a little bit smaller. We got 26.4, and that's equal to 5 times 9.81 is about 49.05. And then we have HF minus 1.5. Now we're going to go 26. We're going to divide both sides by 49.05 first. Oops, 0.5. And when we do that, we get 26.4 divided by 49.05. On this side, we get a value of 0.538226. And that's going to equal HF minus 1.5. Now, we're going to isolate for HF by adding 1.5 to both sides. And when we do that, we have this formula as our final isolated HF. We take that value, we add 1.5 to it, and the final height for this question must have been about 2.04 meters. And so this is a more complicated version of the potential energy. So the next problem says a rubber band with a spring constant of 17.38 newtons is stretched by 5 centimeters. What is its elastic potential? So because it's asking for elastic potential, we can jump right to the elastic potential formula, which is half kx squared. K would be the spring constant, and that's given to us over here of 17.38 newtons per meter. So this one is relatively straightforward. We could just sub in all the given values, and that ends up being 17.38 newtons per meter. And then the x is 5 centimeters, but remember it has to be converted to meters, so we're going to divide that by 100. And that ends up being 0.05 meters. And so what we do is we plug that into our calculator, and we go 0.5, because it's the same thing as writing half. So 0.5 multiplied by 17.38 multiplied by 0.05, and that gives us a relatively small elastic potential. But remember, it's a rubber band. It's a small piece of elastic, so it shouldn't have many joules. So 0.4345 joules of elastic potential. Now, if you notice here, I'm not being so particular with the digits, but on the assignment and unit test, we will ask for digits this time. So just out of practice, if I wanted this in 3 digits, then you would just write 0.435 joules. Okay. All right, let's do the last question here. So we're going to use the same rubber band with the K of 17.38. So it says if that same rubber band gained an elastic potential of 70 joules, how far was it stretched? Okay. So it's not saying in reference to the original stretch. So we're just going to assume that the gain is just in total. So it's going to be E is equal to half kx squared. And the E is given to us as 70 joules. Half the K is going to be in reference to the previous elastic band, so that's going to be 17.38 newtons per meter. And then the x squared, well, that's exactly what we're trying to solve for. So we could do this a couple of ways. You could cross multiply the 2 over here, and then that gives us 270J is equal to 117.38, and then x squared. And this one here is essentially negligible, so we can even just get rid of it. And then what we could do next is divide both sides by 17.38, and that would get rid of it on the right side. And then what we're going to do is we have, because right now we have 270 joules over 17.38 equal to x squared. What we're going to do is root both sides so we can just get x. And when we plug that into our calculator, we end up getting a value of about, and make sure to put all brackets in here when you do this, we end up getting a stretch, or an x, of about 2.8, if we're going to do 3 digits, 2.84 meters. So that's potential energy. What I encourage you guys all to do right now is try some of the worksheets.